Hello friends, welcome back to my channel Computer Engineering Made Easy, and I am Anindita. In today's tutorial, I will be discussing about the concepts of multidimensional arrays using static allocation. So please stay tuned. A multidimensional array is an array which has got multiple dimensions. For example, 2-dimensional array, 3-dimensional array, even n-dimensional array may exist in the computer's memory. For example, in a 2-dimensional array, there exists 2 dimensions, one along the row and another along the columns of the array. So this is what a 2-dimensional array looks like. The indices of the array ranges from 0 to n along the 2 directions. In order to declare this 3x3 array, we need to write int a 3, 3. Here a is the name of the array, whereas 3 and 3 denotes the number of rows and the number of columns in the matrix. Next, in order to identify a specific position marked by the star, we simply need to write the row number and the column number of the specific location. For example, in this case, the star resides in the 1th row, 2th column of the matrix. Hence, we simply write A12 to refer to that particular position. Now let us take a look at a 3-dimensional array. In a 3-dimensional array, we have multiple 2-dimensional arrays residing in multiple layers. Let us call this array B. And in order to declare this array B in the computer's memory, we have to specify the total number of rows, number of columns, and number of layers in the matrix B. This is what a 3-dimensional array looks like. So since we have 2 layers here, we are going to have 2 3x3 matrices or 2 3x3 2-dimensional arrays, and we will call each of these layers, or we will number each of these layers as 0, 1, 2, n, where n indicates the total number of layers in the array. Each of these 2-dimensional arrays in individual layers is going to have 3 rows and 3 columns, because in the matrix B, we have specified the number of rows and columns as 3. Here, the rows mark the first dimension, while the columns mark the second dimension, and the number of layers mark the third dimension in the array. Now, if we have to identify a specific location in the 3-dimensional array, say for example marked as the asterisk symbol, we will simply write B, 1, 2, and 1. Here, the first one indicates the row number of the position holding the asterisk, 2 indicates the column number of the position holding the asterisk, and 1 indicates the layer number or the depth of. Now, why do we need to learn about the concepts of multidimensional arrays? Let us take an example. Say for example, let us consider the railway timetable. We have all seen a railway's timetable, right? How does it look like? It's a tabular structure where we have got multiple rows and multiple columns. In the multiple columns that we have, the most important are the time at which the train leaves or enters the station. Second thing is the up train number, whether it's in the up direction, or the third column indicates whether it is in the down direction. Individual rows stores the entry corresponding to individual trains. In order to represent this kind of information in the computer's memory, which kind of data structure do you think will be the most appropriate one? Of course, it is going to be a 2-dimensional matrix, isn't it? So that is why we need 2-dimensional arrays to represent this kind of information. Now let us say we take the second example where we want to store the marks of n subjects of m students into the computer's memory. So in order to do so, we can again consider a 2-dimensional array where individual rows will indicate the entries corresponding to each student, while the column numbers will indicate the roll number of the student along with the individual subjects. Now let us take a look at the third example. In this example, we look forward to store the individual characters present in each line, each paragraph, each page of a book into the computer. In this case, what kind of array do you think will be most appropriate? Well, it will be a three-dimensional array. We can map the individual pages of the book to individual layers of the matrix, and for each page we can identify the row number and column number of the individual characters and store them accordingly in their corresponding position in the corresponding layer of the matrix. Okay, so now that we have learned about the concepts of two-dimensional and three-dimensional arrays, how exactly do you think they are stored in the computer's memory? Well, the answer is linearly. No matter whatever the dimension of the array is, all arrays are stored in the computer's memory linearly. Two-dimensional arrays are usually represented using two methods. The first one is called a row major order, which is usually followed in languages like C, C++, or Java. And sometimes a second method, that is called a column major method, is used to represent the arrays in the computer's memory. Languages like MATLAB uses this column major order. Say for example, we have a 3x3 array which stores the elements as 10, 20, 30, 40, 50, 60, 70, 80 and 90 row-wise. In case of row major ordering, these entries are stored row-wise in the computer's memory in the form of a single-dimensional array as shown in the figure. Now, if we display the addresses of each and individual cells of this particular two-dimensional array, we will find that if the address of the cell holding 10 is 100, for example, the address of the cell holding 20 will be 104. For 30, it will be 108, and for 40, it will be 100C. That means in case of hexadecimal addressing, 108 plus 4 is going to give us 100C. Accordingly, the next memory cell, that is the 50th cell, the cell holding the value 50, will have the address 10F. Now, since we are dealing with an integer array, the individual cells will be taking up 4 bytes of memory. Accordingly, the addresses of each and individual cells will be spaced by 4 bytes. Similarly, in case of a column major order, if we check out the memory addresses of the individual cells, we will find that if 10 is located in memory address 100, 40 will be located in memory address 104, and 70 will be located in memory address 108, and so on and so forth. So, for row major ordering, the entries are stored in the computer's memory row-wise, whereas for column major ordering, the entries are stored in the computer's memory column-wise. We will learn more about them in a separate video called row and column majoring in case of arrays. Now let us take an example and see how we can use a two-dimensional array to calculate the transpose of a matrix. Let us consider a matrix A such that the row entries of A are 1, 2, 3, and in the next row we have 4, 5, 6. The order of this matrix is 2 cross 3. So, if we try to find the transpose of this matrix A, say A dash, it is going to be of order 3 cross 2. In A dash, we will have 1, 2 and 3 in the first column, while we will have 4, 5 and 6 in the second column. Now, we can use a two-dimensional array of order 2 cross 3 called small a to represent this matrix A. The array is going to have 1, 2 and 3 in its 0th row, whereas it is going to have 4, 5 and 6 as entries in the 1th row. Now if we try to find the transpose of this matrix, then the order of the transposed matrix should be 3 cross 2. Accordingly, we need an array that will be 3 by 2 in size. Let us call this array small b. Small b is going to have 1, 2 and 3 in its 0th column, whereas 4, 5 and 6 will reside in the 1th column of b. Now let us take a look at the program that we need to write in order to execute this concept. Right at the beginning, we need two arrays A and B of dimensions 2 cross 3 and 3 cross 2. Here, A will be responsible in storing the original matrix that will be taken as input from the user, while B will be responsible for holding the transposed matrix. Note that since the order of the matrix is not same, that is, the number of rows and number of columns of the original matrix is not same, finding the transpose is going to change the dimension of the array. Hence, we need two separate arrays for this implementation. Once the arrays has been declared and entering data has been requested to the user, we move on to the for loop. Right at the beginning, I and j are both set to 0 and the user is asked to enter the value of aij, that is a00th position. Let the user enter the value 1. So accordingly, 1 gets stored in the a00th position. Next, the value of j gets incremented by 1 to 1 and the user enters 2. So 2 gets stored in the 1th position. Similarly, when j further gets incremented to 2, the user inputs 3 and 3 gets stored in the array. Next, the value of j gets incremented to 3. However, 3 less than 3 condition becomes false. Hence, the control jumps back to the ith loop and I gets incremented to 1. J again gets reset to 0 and the user now enters value 4 for the 1/0th position of the array, which gets stored in the 1/0th position. Next, j again gets incremented to 1 and 5 gets stored as per user input. Finally, for j value 2, 6 is entered by the user, which gets stored in the matrix. When j again becomes 3, the condition for j less than 3 becomes false and hence we break out of the loop. Now I gets incremented to 2 and since I less than 2, this condition also becomes false. We jump to the for loop for finding the transpose of the matrix. Now you need to be very careful when finding the transpose of the matrix because the row numbers and the column numbers will get interchanged. So we have to be very careful about what will be the maximum value of the row number and what will be the maximum value of the column numbers. Since the matrix A had 2 rows and 3 columns, the matrix B should have 3 rows and 2 columns. That is just the opposite. Hence, when we try to store the value of the matrix A into the matrix B while changing the rows and columns, we need to be careful about the positional indexes. Now again we are initializing the value of I to 0 and j to 0. And inside the loop, we execute bji is equal to aij. Ji are both equal to 0, hence b00 will be equal to a00. Accordingly, the value 1 gets copied into the 00th location of the matrix or array B. Next, the value of j gets incremented to 1 and now we try to execute b10 is equal to a01. So you see the value in the 0th row 1th column of A now gets stored in the 1th row 0th column of the B matrix. That is, the row now gets copied into the column. Accordingly, when j gets incremented to 2, 3 gets copied from A02 to B20. Note that the line bji is equals to aij plays a very significant role over here. We need to be very careful about the extent of the values of the variables I and j before using this particular expression. As j gets incremented to 3, we find that the expression j less than 3 becomes overruled. Hence, the control jumps back to the for loop where the value of I now gets incremented to 1 and j gets reset to 0. Accordingly, B01 equal to A10 gets executed. This means that the value 4 gets copied from the A10th position to B01th position. Similarly, the other two values, that is 5 and 6, also get copied from the matrix or array A to the designated positions in the array B. So with that, we get the transpose of the array A in the array B. Now, instead of the statement Bji equal to Aij, if we had written Bij equal to Aji, then what would have happened? Note that the maximum value of I is going to be 1, while the maximum value of j is going to be 2. So considering the maximum values of I and j, if we try to execute the statement Bij equal to Aji, we basically execute B12 is equals to A21. Now note that the array B has got only two columns, 0 and 1. It has no column with the index 2. Hence, this is going to give rise to a syntax error. This statement would have worked if we were dealing with a square matrix. But in this case, in case the matrix is not square, we have to be extra cautious about this particular statement. Moving on to the displaying module, note that the range of the variable I in this case is from 0 to 3, unlike the previous cases where it was from 0 to 2, and also the value of the variable j ranges from 0 to 2 instead of 0 to 3 like the previous cases. This is because the matrix has already been transposed, and now we are going to display the transposed matrix. The value of I is again reset to 0 along with the variable j, and we display the content of Bij, which in this case is 1. Next, the value of j gets incremented to 1, and again we display the content of the 0,1th location of the matrix B, that is 4. Next, we break out of the for loop because the value of j becomes 2 and 2 less than 2 becomes false, and we encounter the printf statement, which brings us to the new line. The value of I then further gets incremented to 1, and accordingly for values of j ranging from 0 to 1, we display the values 2 and 5. Again, the value of j becomes equal to 2, so we break out of the inner for loop, and with the printf \n we come to the new line. Next, the value of I again gets incremented to 2, and with the range of j from 0 to 2, we display the values 3 and 6. Finally, we break out of the for loop, the outer for loop, because the value of I now becomes equal to 3, and on returning 0 to the main function, we come to the end of the program. Moving on to the next example, that is addition of two matrices using double dimensional arrays. Now let us take an example of two matrices, say A and B, where A is equal to 1, 2, 3 and 4, 5, 6, while B is equal to 3, 4, 5 and 2, 1, 0. We add the two matrices A and B and store the outcome in the matrix C. Note that the order of the matrix A and B are both 2 cross 3, hence order of the matrix C will also be 2 cross 3. The outcome of the matrix C is going to be 1 plus 3, 2 plus 4, 3 plus 5, 4 plus 2, 5 plus 1 and 6 plus 0. In order to store the matrix A into an array, we need a 2 cross 3 array. Hence, we have the array A, which has got 2 rows 0 and 1 and 3 columns 0, 1 and 2. The values of the matrix A get stored in the corresponding positions of the array A. Similarly, the matrix B gets stored in a corresponding 2 cross 3 array mentioned by the name small b in the computer's memory. Now let us take a look at the program that we need to write in order to implement this phenomenon. We need 3 arrays, each of size 2 cross 3, in order to store the 3 matrices A, B and their sum, that is C. Next, we look forward to take the values of the matrix A as well as matrix B as input from the user. The first set of for loops are responsible for taking the entries of the matrix A row-wise and storing it into the array A. Here, the value of I ranges from 0 to 2, indicating the rows, while the values of j ranges from 0 to 3, indicating the columns. Since j is the inner loop, we are basically storing the values row-wise. So for varying values of I and j, we take values as input from the user and accordingly we store them in the appropriate position of the array. We then execute the next set of for loops which are responsible for taking the input corresponding to the matrix B into the array small b. Now moving on to the addition part, here the variables I and j run as loop variables from the range 0 to 2 and 0 to 3 respectively. Basically they traverse all the 3 arrays row-wise, and the third statement, that is Cij equal to Aij plus Bij, basically takes the values in the same position of matrix A as well as B, adds them up and stores the resulting value in the same position of the matrix C, just like as we do in case of normal matrix addition. Therefore, for I equal to 0 and j equal to 0, the values corresponding to the 0, 0 position of matrices A and B get added, that is 1 and 3 get added to get the value 4, which is then stored in the 0, 0th position of the matrix C. Next, j being the inner loop, its value gets increased from 0 to 1. This means now that we are referring to the position 0, 1. So accordingly, the values in the 0, 1th position of the matrices A and B, that is 2 and 4, get added and the resulting value, that is 6, gets stored in the 0, 1th position of the matrix C. Next, the value of j further gets incremented from 1 to 2 and accordingly the values in the 0, 2th position of the matrices A and B, that is 3 and 5, get added to give the resulting value as 8, which is then stored in the 0, 2th position of the matrix C. The value of j further gets incremented to 3 and the condition j less than 3 becomes false. Hence, the control goes back to the ith loop and the value of I now gets incremented to 1. The value of j, however, gets reinitialized to 0 and increases gradually as the loop executes. For each iteration of the variable j, the entries corresponding to the ith row jth column of the matrices A and B get added and the resulting value gets stored in the corresponding position of the matrix C. That is, 4 plus 2 becomes equal to 6 and the 6 gets stored in the 1th row 0th column of the matrix C. Similarly, 5 plus 1 becomes 6 and this 6 also gets stored in the 1th row 1th column of the matrix C. Finally, 6 plus 0 gets added to 6 and this 6 also gets stored in the 1th row 2th column of the matrix C. All this happens with increasing values of j. Finally, we move on to the display section of the program where we again run the loops for I equal to 0 to 2 and for j equal to 0 to 3. Even in this case, the value I the value of the variable I indicates the row number, while the value of the variable j indicates the column number of the matrix. We traverse the matrix C row-wise and we continuously display the content of the ith row jth column of the matrix C. The printf statement within the for j loop, as we come out of the inner for loop, we realize that the first row of the matrix has already been executed, and therefore in order to bring the control to the next line, we include this printf \n statement right after the inner for loop. On executing this statement, the control jumps to the next row and the increment of the variable I occurs, which indicates that we have moved on to the next row. With that, we come to the end of the matrix addition problem. Now we need to put ourselves into the shoes of two different categories of people. The first one is an engineer who is designing this problem, which is actually going to be your profession. And the second one is the user. The user is basically a layman who will be interested in purchasing your software because he wants to add two matrices. Now the program that we have written, will this be sufficient to solve the matrix addition problem of any order? Definitely not, right? This particular problem or this particular program that we have written will be able to add two matrices of the specific order 2 cross 3. If the matrix size is greater than this or less than this, or the order is something different than this, the program may not be able to perform the matrix addition operation correctly. Hence, we can go for two options. As per the first option, we can declare an array size which is significantly high. This will allow us to declare arrays or use arrays for matrix addition where the order of the matrices is less than the array size. But how high will this be? We are not aware of what can be the maximum matrix size that the user will want to multiply. Hence, two things may happen. Either the user might choose to multiply two matrices of significantly low order, say 2 cross 3, 1 cross 4. In such case, significant amount of memory space will get wasted. And the second option can be, even though we consider that we are giving a huge size to the array, the user might choose to multiply two matrices which are of even higher order. In that case, the memory will run short and the program will be of no longer any use to anybody. Hence, we can go for the second method, which provides a more customized approach. This is called the dynamic memory allocation. So therefore, using this method, we can create the arrays dynamically based upon the input provided by the user. So we can ask the user what will be the size of the arrays that the user might want to multiply, and based on that, at runtime we create arrays. This is what is called creating arrays or using arrays using dynamic memory allocation. With that, we come to the end of our today's lecture. Please stay tuned for our upcoming lecture where we will be discussing the concepts of dynamic memory allocation for arrays. Thank you for being there. Please like, share and subscribe to my channel if you like it.